Latent heat is the energy per unit mass that must be gained or lost by a substance in order for it to undergo a phase change, such as changing from a liquid to a solid, or from a gas to a liquid. Latent heat is expressed using the variable capital L. In SI units, latent heat is expressed in joules per kilogram, while in English units, latent heat is usually expressed in units of BTU per pound, or British thermal units per pound. The conversion factor is 1 joule per kilogram is equal to 4.3 times 10 to the minus 4 BTU per pound. Another common unit for expressing latent heat is calories per gram. 1 joule per kilogram is equal to 2.39 times 10 to the minus 4 calories per gram. Note that the phase change process occurs at a constant temperature. Furthermore, the phase change process is a reversible process. This means that the amount of heat or energy per unit mass that needs to be gained to allow a given phase change to occur is exactly equal to the amount of heat that needs to be lost to reverse that phase change. For example, the amount of heat gain required to melt 1 kilogram of ice is exactly equal to the amount of heat loss required to freeze 1 kilogram of water, or 3.33 times 10 to the power 5 joules. There are 3 main latent heat types that are associated with 3 types of phase changes. The latent heat of fusion is the heat associated with the change of a solid into a liquid, or vice versa. The latent heat of vaporization is the heat associated with the change of a liquid into a gas, or vice versa. The latent heat of sublimation is the heat associated with the change of a solid into a gas directly without passing through the liquid phase, or vice versa. The actual amount of heat in joules required to change the phase of a given pure sample is equal to the mass in kilograms of the sample, times the latent heat associated with the phase change in joules per kilogram. The latent heat of fusion is the energy per unit mass that must be gained to melt a solid to form a liquid, or that must be lost to freeze a liquid to form a solid. The latent heat of fusion is also called simply the heat of fusion, and is expressed by the variable capital L subscript F, and has units of joules per kilogram. The melting of a solid to form a liquid, or the freezing of a liquid to form a solid, both occur at the same constant temperature, which is called the melting or freezing temperature. The freezing temperature is expressed by the variable capital T subscript F. The freezing temperature is a physical property of any given pure substance. Both the heat of fusion and freezing temperature are functions of the ambient pressure. The latent heat of vaporization is the energy per unit mass that must be gained to evaporate a liquid to form a gas, or that must be lost to condensate the gas to form a liquid. The latent heat of vaporization is also called simply the heat of vaporization, and is expressed by the variable capital L subscript V, and has units of joules per kilogram. The boiling of a liquid to form a gas, or the condensation of a gas to form a liquid, both occur at the same constant temperature, that is called the boiling point. The boiling point is expressed by the variable capital T subscript V. The boiling point is a physical property of any given pure substance. Both the heat of vaporization and boiling point are functions of the ambient pressure. Sublimation is the transformation of a solid into a gas, or vice versa, without passing through the liquid form. The common substance that undergoes sublimation at room temperature is solid carbon dioxide, or CO2, which is more commonly known as dry ice. When dry ice is heated to room temperature by dropping it into a glass of water that is at room temperature, it sublimates into gaseous CO2, as seen in this simple experiment. The reverse process occurs when water vapor changes from the gaseous phase directly into a solid, to form frost on a cold solid surface, such as the windshield of a car on a cold winter night, or the coils of a refrigerator. The latent heat of sublimation is the energy per unit mass that must be gained to transform a solid into a gas, or that must be lost to transform the gas into a solid, without passing through the liquid phase. The latent heat of sublimation is also called simply the heat of sublimation, and is expressed by the variable capital L subscript S, and has units of joules per kilogram. Both the sublimation of a solid to form a gas, or of a gas to form a solid, occur at the same constant temperature that is called the sublimation temperature. The sublimation temperature is expressed by the variable capital T subscript s. The sublimation temperature is a physical property of substances that undergo sublimation at a given pressure. Both the heat of sublimation and sublimation temperature are functions of the ambient pressure. Shown here is a plot of heat per unit mass versus temperature for water at atmospheric pressure. The x-axis has units of kilojoules per kilogram, while the y-axis has units of degrees Celsius. We arbitrarily set the heat per unit mass to 0 at a temperature of -50 degrees Celsius, at which the water is frozen as ice. We can then study how much heat per unit mass is required to transform the ice into steam, and how the temperature of our sample changes as a function of the amount of heat added. We are going to assume in our analysis that the specific heats of ice, liquid water, and water vapor are all constant and are not functions of the temperature. This assumption is not exactly true, but it will only introduce a small error into our calculation, and it will greatly simplify our analysis. You can perform this experiment yourself by slowly heating a block of ice, and observing how its temperature changes during its transformation into water vapor. The heating must be done slowly and uniformly, to ensure that the entire sample is always at roughly the same temperature. When the ice is heated, assuming the specific heat of ice is constant, its temperature increases linearly with the amount of heat per unit mass that is added. The temperature of our sample increases by 50 degrees Celsius, from -50 degrees Celsius to 0 degrees Celsius. The amount of heat per unit mass required to raise the temperature of the ice by 50 degrees is equal to the specific heat of the ice, times the final temperature T2, which is equal to 0, minus the initial temperature T1, which is equal to -50. Using a Cp value of 2.05 kilojoules per kilogram Kelvin for ice, we get a heat per unit mass value of 102.5 kilojoules per kilogram. As we add more heat to the ice that is at 0 degrees Celsius, it starts to melt into liquid water. As the ice is melting, its temperature remains constant at 0 degrees Celsius, until all the ice in our sample has melted. The amount of heat per unit mass that is required to melt all the ice is equal to the latent heat of fusion of the ice at atmospheric pressure, or 334 kilojoules per kilogram. When the liquid water is heated, assuming the specific heat of liquid water is constant, its temperature increases linearly with the amount of heat per unit mass that is added. The temperature of our sample increases by 100 degrees Celsius, from 0 degrees Celsius to 100 degrees Celsius. The amount of heat per unit mass required to raise the temperature of the liquid water by 100 degrees is equal to the specific heat of water, times the final temperature T4, which is equal to 100, minus the initial temperature T3, which is equal to 0. Using a Cp value for liquid water of 4.1813 kilojoules per kilogram Kelvin, we get a heat per unit mass value of 418.13 kilojoules per kilogram. As we add more heat to the liquid water that is at 100 degrees Celsius, it starts to boil and form water vapor. As the water is boiling, its temperature remains constant at 100 degrees Celsius, until all the water in our sample has been vaporized. The amount of heat per unit mass that is required to vaporize all the liquid water is equal to the latent heat of vaporization of water at atmospheric pressure, or 20 to 60 kilojoules per kilogram. When the water vapor is further heated, assuming the specific heat of water vapor is constant, its temperature increases linearly with the amount of heat per unit mass that is added. Assuming the final temperature of 150 degrees Celsius, this implies an increase of 50 degrees Celsius. The amount of heat per unit mass required to raise the temperature of the water vapor by 50 degrees is equal to the specific heat of the water vapor, times the final temperature T6, which is equal to 150, minus the initial temperature T5, which is equal to 100. Using a Cp value for water vapor of 2.08 kJ per kilogram Kelvin, we get a heat per unit mass value of 104 kJ per kilogram. Contrary to intuition, what makes us perceive hotness or coldness is not temperature, rather it is heat flow. Consider the following experiment. We place a metal tray and an empty cardboard box inside the freezer, and leave them inside overnight to make sure that the temperatures of both become equal to the freezer temperature. Next we open the fridge, and take the metal tray and cardboard box out of the freezer. We notice that even though both objects are at the same temperature, the metal tray feels colder than the cardboard box. This is due to the fact that the metal tray conducts heat at a higher rate from our hand than the cardboard box, due to the tray's higher thermal conductivity. Since the heat from our hand moves quickly from the surface of the tray to its core, the surface of the tray remains colder to the touch for longer time period than the surface of the cardboard box. Furthermore, objects that have a higher specific heat would also remain colder for longer time period when we touch them, since they require more heat to flow into them in order to raise their temperature to that of our hand. We conclude that our perception of something as being hot or cold depends on the rate at which it draws heat from or delivers heat to our skin. Of course, the heat flow Q from the object to our skin depends on the temperature difference between our skin and the object, but as we have just seen, it also depends on other factors, such as the specific heat of the object and its thermal conductivity.